3, in which we'll be talking about electromagnetic and mechanical waves. So we have, so let's look, we have two types of waves, right? We have longitudinal waves and transverse waves. So longitudinal waves are where the particles oscillate back and forth in the same direction as which the wave travels in. So if the wave travels right, then the particles will oscillate right and left, or like back and forth in that same direction that the wave travels in. So that's just how longitudinal waves work. And now if we look at transverse waves, the particles will oscillate up and down perpendicular to the motion of the wave. So if we're thinking of so I mentioned up and down because a lot of people think of waves traveling in the horizontal direction. So if we're thinking of a wave traveling right again, the particles will now oscillate like this. So it will oscillate up and down. In that sense, it will be perpendicular to the motion of the wave. So in that sense, if the wave was traveling upwards now, the particles wouldn't oscillate up and down because then they would be in the same direction as the motion of the wave. The particles would oscillate back and forth like this. So that's just how that would look like. So transverse, they will oscillate perpendicular. Longitudinal, they will oscillate in the same direction. Now if we're looking at the role of the medium and the transfer of energy, mechanical waves, they rely on particle interactions to transport energy with no mass transfer. So if mechanical waves rely on particle interactions, that means they require a medium to transfer. Whereas things like electromagnetic waves, they do not require a medium to propagate, or basically to, in terms of propagation means like for it to continue moving forward, basically. So electromagnetic waves, they do not require a medium. That's quite important to remember. And if you want to like conceptually think about this, then, have a think about light traveling from the sun to the earth, right? If we're thinking about light traveling from the sun to the earth, is there particles between the sun and the earth? Well, no, it's in space, right? So there's a lack of particles. And so light still, which we now know, light is an electromagnetic wave, and we know light is emitted from the sun and it reaches earth. So it travels in a vacuum, so it does not require a medium to travel. And electromagnetic waves are, by the way, transverse waves, so they do not require a medium to go through, like they don't require a medium to propagate. And another thing that you would need to remember is that all electromagnetic waves, they all travel at light speed, which we now denote as a variable c, and it's 3 times 10 to the power of 8 meters per second in a vacuum. So this value, 3 times 10 to the power of 8 meters per second, a fair bit of warning, you'll be encountering that quite often, not just in the module 3, but also later on in module 7 and 8 in physics, you'll encounter a lot of stuff about light. So that value itself, you'll be encountering it quite often. Okay, so that is just a summary of electromagnetic waves and mechanical waves. Once again, important thing to take away is the direction that the particles oscillate at, and the fact that electromagnetic waves, they don't require a medium to propagate through, and that they all travel at light speed which is this speed within a vacuum. And then, mechanical waves, they rely on particle interactions to, this is also important as well. They transport energy, but they don't transfer mass or matter, basically. So that's what's important there. So this is just a visual representation of a transverse wave and a longitudinal wave. We have both over here. So a longitudinal wave here we see, so the palm here is we're pushing it forward, right? We're pushing it forward and then we're retracting it back to the original position. So if my hand is here, I take the slinky, I tape it to the end of the wall, and I push my hand like this. So I'd push it, then retract it back to its original position. That's what these green arrows are showing. And I'd keep repeating that motion. And what you'd see is, compressions over here and rarefactions, which is like the lack of compression over here. So this, you can see over here that the coils in the slinky get bundled up in basically the bundles of slinkies reach the wall in waves, right? So that's kind of like the verbal way of representing it. And what we're ending up creating is we're creating a longitudinal wave, because if you think about the oscillations of the particles now, in this sense, the oscillations will be represented by the compressions and the lack of compressions over here, which is called the rarefaction. So the compressions and the rarefactions, that shows the direction of oscillation. And if we're looking at the direction of oscillation, it's traveling in the horizontal direction, right? And now what direction is the wave traveling in? Well, the wave, we're pushing this way, right? We're pushing the wave, so we're inducing a wave in the horizontal direction as well. So the particles in this case are oscillating in the horizontal direction. We're inducing a wave in the horizontal direction. that means that the particles are oscillating in the same direction as the motion of the wave, and so it becomes a longitudinal wave by definition. Now let's look at a transverse wave. So another thing is that this prac, I did this in school, so you'll probably do this in school, where they'll bring out a bucket of slinkies and they'll, like, maybe make you get in pairs, or like you'll get each an individual slinky, and you'll basically have to test out or like induce a transverse and longitudinal wave yourself. So now let's induce a transverse wave where the oscillation has to be, now if you think back to the previous slide, it has to be perpendicular to the direction of motion. So now let's induce a wave that goes horizontally again. So if the wave now travels horizontally and the particles, for it to become a transverse wave, have to travel perpendicularly, that means the particles in this case have to travel up and down. So in that sense, what we do is now we move our hand like this. So we move our hand up and down, and as you can see, that creates crests and troughs like this. And this then induces, the particle in this case goes up and down and up and down and up and down. So the particles oscillate up and down, which is perpendicular to the direction of motion of the wave, which is horizontally. And so now we, by definition, induce a transverse wave. So that's how we would induce a longitudinal and transverse wave in a slinky. So we can introduce both in a slinky, and that's probably why you'll be doing a prac about this in school as well. So now let's look at an electromagnetic wave, right? So you can see here that there's two waves. So an electromagnetic wave is, if you look at the name, right, it's made up of an electric and a magnetic wave. So an electromagnetic wave now consists of both an electric field and a magnetic field. So there's two waves that make up the entire wave, right? Or there's two fields that make up the entire wave. And let's look at the direction of propagation. The direction of propagation is, well, if we think about it from this angle, right, the direction of propagation is, we'll say, into the page. So the direction of propagation now goes into the page. Now, which direction does the magnetic field oscillates in? It oscillates in, so if the propagation direction of the entire wave is into the page or in the z-axis, then the magnetic field now oscillates in the x-axis, right? It oscillates horizontally. And if you think about it, the x-axis is perpendicular to the z-axis. So the magnetic field now oscillates perpendicularly to the direction of propagation. Same with the electric field, because if you look at the electric field now, it is propagating in the same direction, but it's oscillating in the y-axis. So it's oscillating up and down. And so it's also oscillating perpendicular to the direction of motion. So both of them are oscillating perpendicular to the direction of motion. Both of them make up an electromagnetic wave. And so the electromagnetic wave, by definition now, becomes a transverse wave. So we always come back to this idea of particles oscillating when we're trying to define whether it's a transverse or longitudinal wave. So that's something that's very important to think about here. Now let's think about how to interpret the wave motion. So the waves itself can be modeled in two different ways. So these two graphs that we can get are displacement time graphs and displacement position graphs. And it's very important to know both of these because they tell us different things. So we have different properties of waves. We have wavelength, we have amplitude, and we have period. So these are two different things that we can, different properties basically that we can extract from the information we get from a wave. And these in total allow us to find other properties like velocity and period of rotation and stuff like that of a wave. So if we think about displacement versus time graph now, so it's very important to identify which one it is. So we have displacement versus position and displacement versus time graph. So let's look at the graph on the left, the displacement versus time graph. So if we're looking at the displacement versus time graph, let's look over here, right? The displacement of a single particle in the medium over time. That's what the displacement versus time graph is showing, the displacement of a single particle in the medium over time. So if we look at that one now, we can see that the displacement of the particle increases, then it comes back down to a zero displacement point, then it decreases, and then it comes back to a zero displacement point, and then it keeps repeating, right? So the difference between this midline and the highest or the furthest points that the displacement travels is what we call as amplitude, and it's denoted by A. So it's amplitude and it's denoted by capital A. And the difference or the distance, the length between, if we're measuring this now, the difference between the distance, between one crest, which is the one top point, and the second crest, which is the second top point, so two peaks basically, the distance between two peaks will give us capital T, otherwise known as period. So it will give us a function or a quality, a property of wave called the period. And we'll also get amplitude over here. And we'll go through a little bit about what these properties mean a bit later. So we have displacement versus time graphs, and now let's go into displacement versus position graphs. So displacement versus position graphs, they tell us the displacement of various particles as we change their position along the median at a given point in time. So it's not now just a single particle in the median, it's the displacement of various particles as we change our position along the median. So we're changing our position along the median at any given point in time, or at a certain given point in time, and we're checking the displacement of various particles. So yeah, we basically we freeze the wave and then we travel through the medium to find the displacement of the various particles. So this is kind of like what the, if you think of your classical like, or your generic like image of a wave, and if we think of like, if you've seen oscilloscopes or, other types of machinery, they'll have like, waves looking like this. And then they'll be like, you might have previously encountered wavelength before. If you've previously encountered wavelength labeled on a wave graph that looks like this, what you're going to be looking at is a displacement versus distance graph, because that wave is essentially frozen in time. So it's no longer displacement with respect to time because the time is frozen. But what we're looking at is the displacement of the entire wave as we travel along its medium. So as we travel along its medium, that's denoted by the distance, x. So let's look at the properties we can gain from the displacement versus position graph. So displacement versus position graph, again, we have the distance between the peak point or the crest and the midline is given by amplitude. Same with the distance between the midline and the trough over here. That's also given by amplitude. Another thing is wavelength. So we can now find wavelength, which is the length of one wavelength essentially, like by naming conventions, it's in the length of one wave, and we can find that by finding the distance of two crests or two peaks and the distance of two troughs or two peaks again. And we can also find the wavelength by looking at the distance between this 0 point and this 0 point. So essentially two identical sectors of the wave. We find the distance between these two identical sectors of the wave, and by doing that we find the wavelength. So that's the displacement versus position graph versus the displacement versus time graph. And I have to warn you guys that a lot of students, including myself, make the mistake where we look at a wave graph and we instantly think yes, it's probably going to tell us wavelength, and we ignore the axes. So always make sure to check the axes to check whether it's time or distance on the x-axis. If it's time, then you're not going to be getting wavelength over here, you're going to be getting period. So a lot of people might get stuck on questions because they've already given us a wavelength and they haven't given us a period, but they want us to find a period, but we don't realize that we can get period by just doing this. So yeah, it's just an area that a lot of people might get confused at. So just make sure to identify whether it's a displacement versus time or a displacement versus position graph. So now moving on, let's look at the different properties of the wave. So I already talked about the amplitude, right? So it's essentially another way to describe the amplitude is we can think about it as the max disturbance from the midpoint. So yeah, if we're looking at the trough and crest of a wave that I was talking about earlier as well. So the trough is like this black part. So the black part will be given by the dip. So as it goes beneath the midline, that becomes the trough. So this point over here that my cursor is at would become the trough. And if we're looking at the crest of the wave, the crest would become the peak, or this white line. That would become the crest, so over here. And this yellow line, right? What is this yellow line? Well, a lot of graphs, you'll see wave fronts. So you see wave fronts. Wave fronts are basically, it basically shows you the direction that the wavelengths are moving at. So a wave front, right? It will be, so if this wave was over here, in real life, right, I'm going to explain it like this. In real life, there's not just going to be a singular wave traveling, right? It's most likely going to be a bundle of waves traveling. So there's not just going to be one, there's going to be like a lot of waves traveling, right? And they're all going to be like next to each other. So we need to identify the wavelengths of these, right? So the wavelength is, the wave front, right? The wave front basically identifies this peak, this crest over here. It just draws a perpendicular line through the bundle of waves that are traveling like this. And so it draws a perpendicular line between the crests of these bundles of waves. And so we get this yellow line. So if we're now looking at this image over here, you can see we have crests over these white lines over here. And what it's doing is it's drawing a perpendicular line over here. And the wavefront is facing this way. So we know that the wave is traveling this way, which is again perpendicular to the direction of the wavefront. We know that's the direction that the wave is traveling at. So that's kind of what the wavefront is showing. And yeah, we'll see these wavefronts in further diagrams. So we talk about wave properties, so we'll encounter these a bit later. But yeah, so we talked about amplitude so far, we talked about crests and troughs, and we talked about wave fronts. Now let's talk about wavelength. So wavelength, if we go back over here, we talked about wavelength over here as something that we'd find in a displacement versus position graph. So going back over here now, the wavelength given by lambda is by definition, the distance between two successive identical parts of a wave. So peaks or troughs work, but also, this midpoint and that midpoint, they also work. So two identical parts of the wave, what is their distance between them? Well, that is the wavelength. Now we also have frequency. So frequency is the number of waves that pass a point in a second. And if we want to find frequency, what we do is we do frequency, which is denoted by this symbol F, equals 1 over T. And now where have we seen capital T before? Well, if we go back to this wave over here, we see capital T as, well, the distance between two identical parts of a wave for a displacement versus time graph. So this is how we find period, right? And so frequency is equal to 1 over period. So that's what frequency is. And it's, by definition, the number of waves that pass a point in a second. Now let's look at the capital T. So capital T is the period. And by definition, the period is the time interval for one complete oscillation. So the time it takes for a wave to complete a full oscillation. So it starts its oscillation period over here, and as it completes its full oscillation at the second crest, we can stop the timer, and that time taken will be given as the period. So the units for period will be seconds. The units for frequency will be 1 over seconds, or seconds to the power of, or s to the power of -1, because it's the amount of waves that pass a point in a second. And now if we're trying to find velocity, we do V. So this is the velocity of the wave. So this is the generic formula for the velocity of the wave. V is equal to F lambda. V is equal to frequency times wavelength. So let's think back to our normal velocity equations, right? Let's think to our normal velocity equation. So our normal velocity equations is distance over time, d over t, or s over t, displacement over time, right? Why is this one not a fraction? Why is this a multiplication of two variables? Well, velocity, the units are given by meters per second. It's over a fraction, right? Now let's look at the units over here. Frequency is already something over seconds, right? Seconds to the power of -1, and lambda is given in meters because it's the distance between two identical parts of the wave. So frequency, 1 over so seconds to the power of -1 times meters is going to equal meters per second. So in terms of units, it makes sense, right? We're achieving meters per second either way. And another way of thinking about this is if we're trying to calculate the speed of the wave by using displacement over time, what we do is we do wavelength divided by period, distance over time. Now, what is wavelength divided by period? Well, it's wavelength times 1 over t, which is then equal to wavelength times frequency. So V equals F lambda. That's just a couple derivatives of that actual equation. Now let's also look at the wave number, which is k, and that's like the spatial frequency basically, and k is given by 2 pi over lambda. So that's the equation for the wave number. So these are a couple properties of waves now. So as a summary, we've gone through amplitude, wavelength, frequency, period, and the relative equation. So V is equal to F lambda, F is equal to 1 over t. If these are like, if you're being introduced to them, like if you're just being introduced to these values, then a good thing to, maybe memorize these values is to maybe after this lecture, write down these symbols. So A, lambda, F, and T, and then, close your books, close your notes, and then try and identify what each variable represents and what their meanings are. So that'll get you to a learning method called, spatial repetition. You can, test yourselves with increasing gaps between your periods of testing, and it'll allow you to recall the information that you have heard me talk about, and recall the information that you'd have read in the slides, and by applying this knowledge, it'll solidify it in your memory. So that's a good way of memorizing what each of these variables mean. But yeah, in summary, we've gone through the variables now, and we've also gone through the difference between a displacement time and displacement position graph. So now we can move on to our first question. So question number 1. A detector observes the positive peak of an electromagnetic wave pass by every 0.009 seconds. What is this wave's wavelength? Well, okay, so the way to answer this question now is to look at the values that they've given us. So they've given us the positive peak of an electromagnetic wave passes by every 0.009 seconds. So we have time, which is 0.009 seconds. And what represents time? Well, time is represented by period, right? Period is are represented as time. So if we're looking over here, 0.009 seconds will be the period. So we have period equals 0.009 seconds. And what other information do we have? Well, they don't explicitly give it to us, but implicitly we do know one other variable. And what is that? Well, we know the speed of an electromagnetic wave, right? Because if we go back to our first slide, not our first slide, our first introduction to module 3 slide, what do we know? Well, we know that the speed of an electromagnetic wave is 3 times 10 to the power of 8 meters per second. So what data do we know? Well, we know the speed of an electromagnetic wave. We know V is equal to 3 times 10 to the power of 8, and we know T is equal to 0.009 seconds, and we're trying to find the wavelength, right? So we have over here, so the distance between two graphs, so this is a displacement over time graph, and we have that to be 0.009 seconds. And we have our equation that we're going to use now, V equals F lambda. Why do we use that equation? Well, we're trying to find wavelength, right? And what's the only equation that we know so far that relates the data that we have to wavelength? Well, it's equal to V equals F lambda. Now you might think, right, well, we have period and wavelength, but the equation that we're using is V equals F lambda. There's no period in that. Well, we know the second equation, which is F is equal to 1 over T. So we know T, so we can calculate frequency and we can sub this into this equation to find the wavelength. So V equals F lambda. Now we can find frequency through F equals 1 over T, which is equal to, this should be a capital T, sorry. This is equal to 1 over 0.009 as the frequency. So now we have the frequency of our data. Now we can rearrange the equation, right? So lambda is equal to V over F, which is equal to 3 times 10 to the power of 8 meters per second divided by frequency, which is what we got over here. So 1 over 0.009, and this should give us a value of 2.7 times 10 to the power of 6 meters as our value for wavelength. So another important thing when you're solving these types of questions is to always don't sub it in initially. So we have all this data, right? I could have subbed in a value for velocity and frequency and then, just divided through mathematically. But it's a good practice, especially now to solidify, to only sub in the data at the very end once you have rearranged everything algebraically. So the reason for that is so right now we have pretty clean data sets, but moving on, especially in senior physics as well, the data that you might be given might have very long decimal points, so there might be recurring decimals and stuff. So subbing it initially will be quite a hassle to write down and subtract and multiply and divide by. So you might end up doing mathematical errors or writing errors, so silly mistakes might occur a lot often. So it's a lot easier to just algebraically rearrange this equation like this to make what we want the subject. So we want wavelength, so we made wavelength the subject of the equation. So lambda is equal to V over F, and then we sub all the values in to avoid any silly mistakes that might occur by us miswriting the numbers when we're writing it down and then mistyping it into the calculator and getting it wrong. So we're avoiding all of that by subbing the values in at the very end, to also it gives us a clean answer as well. We get a definite and final answer at the very end. So yeah, that's just a little tip as well. Always sub in the data at the end and rearrange the values algebraically first, and that's a good practice to develop now as well. But yeah, the answer is this. And another important thing is, something that you might also want to do is, if you have extra time, especially for all your questions, write an extra sentence that directly answers the question. So what we have over here is we have lambda is equal to 2.7 times 10 to the power of 6, but to answer the question even better, and this is more effective for longer questions, we can say, therefore, we can write this in English now, therefore, the wave's wavelength is 2.7 times 10 to the power of 6 meters. So we write this in English, but obviously not 2.7 times 10 to the power of 6, but we write, therefore, the wave's wavelength is 2.7 times 10 to the power of 6 meters. So we're directly answering the question with a sentence at the very end, and that's also a good practice to have. So now we can do a second question. So a piano produces a note with a frequency of 450 hertz and a wavelength of 0.75 meters. Calculate the speed of sound, the speed of the note essentially, or the speed of sound. So what do we have so far? Well, we have, what's our given data? We have frequency, we have wavelength. Let's go back to the equation, right? What equation can we use? Well, what do we need first? Well, we need the speed of sound, or the velocity of the speed of sound, the velocity of sound. What equation do we have? Well, we have a velocity for the speed. We have an equation for the velocity or speed that's given by V is equal to F lambda. So what data do we have? Well, they've given us frequency, they've given us wavelength. So it should be a very simple plug in and get an answer question for this one. So going through, we have V equals F lambda, so which is equal to 450 hertz. So hertz is the units for frequency, and it's essentially 1 over seconds basically. So we have V equals F lambda, so frequency is 450 hertz, so 450 times 0.75 meters, and that gives us an overall speed of 3.375 times 10 to the power of 2 meters per second, or 3.4 times 10 to the power of 2 meters per second to two significant figures. So another thing is that for those of you that don't know the significant figure rule, so what you do is you look at your question, right? And you try to look at the shortest amount of significant figures that you'd use in your question. So that the shortest amount of significant figures present in the data that you use to get your answer. So this also applies to if you extract data from the data sheet and that becomes the shortest amount of significant figures, then you'd apply that to this rule. So you look at that shortest amount of significant figures and then you write your answer to that shortest amount of significant figures. So in this case, I use 0.75. How many significant figures? Two significant figures. So what's my final answer going to be? It's going to be in two significant figures. So it'll be 3.4 times 10 to the power of 2 meters per second to two significant figures. Another thing that some schools learned, and I learned this as well, is try to avoid writing your answers to one significant figure. So sometimes they'll give one significant figure. Try to avoid writing to that. But in my experience, it's quite subjective. So some schools do want you to write to one significant figure. Some schools don't want you to write to one significant figure. So make sure to ask your teacher and check, because what's important is right now internal exams are like also your school exams are what matters. So in terms of who's more correct, the rule or the teacher? Well, in this case, the teacher is more correct, because you're trying to impress your teachers and show your teachers that you know the content, because they're ultimately the people marking you right now. So make sure to have a good relationships with your teacher, so you can ask your questions or questions like these to clarify which significant figure or what the rule is for your school. So make sure to check with your teachers before your exams start, just to make sure you don't lose any marks for lowest amount of significant figures. And again, for questions like these, you can write a sentence at the end. So you can say, therefore, the speed of this sound wave or the speed of the note is 3.4 times 10 to the power of 2 meters per second to two significant figures. So you can write another sentence at the end that directly answers this question. So I hope you guys found that question easy. It was just us, subbing in values into the question, not really rearranging it like we did for the previous question. So it wasn't too bad. Now let's move on to the next question. So a 5G tower is being put up next to a block of units. This tower emits microwaves at a frequency of 200 gigahertz. So we automatically know we have frequency. The house inspector is worried about the wavelengths emitted by the tower. If the wavelength is below 15 centimeters, the detrimental health effects can occur should the inspector be worried. So should the inspector be worried? That's kind of indicating for us to find the wavelength. So we need to find if the wavelength is below 15 centimeters, right? So what variable are we looking for? We're looking for wavelength. What variables do we have? We have frequency. What else do we have? Well, think implicitly, right? It's a microwave. What is a microwave? Well, a microwave is a type of electromagnetic radiation. So what do we know about electromagnetic radiations? Well, we know the velocity of electromagnetic radiation to be 3 times 10 to the power of 8 meters per second. So we have the velocity of an electromagnetic wave, and we have the frequency of this electromagnetic wave. We're trying to find the wavelength, and we're trying to see if it's below 15 centimeters, right? Or if it's below or above 15 centimeters to see if health effects can occur. So we have frequency, 200 times 10 to the power of negative 200 times 10 to the power of 9 hertz. We have velocity, 3 times 10 to the power of 8 meters per second. We have wavelength. We don't have wavelength. We're looking for wavelength. So all we have to do is we write out the equation. So V equals F lambda. Another important thing is always make sure to write out your equations, and always make sure to, another important thing is, so how I previously mentioned, always sub in your data at the end. That's also very important if you want to claim back marks for silly mistakes. So sometimes if the answer is wrong, your teacher can give you 0 marks for the entire question. But if you did solve your question algebraically and then you showed them that you correctly rearranged the equation algebraically, then you can only lose 1 mark for that, because that tells the teacher that you only subbed in the values to your calculator wrong. So you calculated error, which is minus 1 mark. But if you use the right equation, so if you showed that you used the right equation and you showed that you arranged that right equation the right way to achieve the variable, so you rearrange this equation to make this wavelength the subject, and then you subbed in the values incorrectly, then you'll get the marks for using the right equation, rearranging the right equation, and you'll lose that 1 mark for just subbing it incorrect instead of losing all the marks. So that's also very important, and another reason why you should always solve everything algebraically and then sub the values in. So what equation are we using? V equals F lambda. Always write this equation out when you're using it. Don't just start with lambda is equal to V over F, because you need to show them that, or you need to show the teachers that you know which equation to use. So we start off by writing V equals F lambda, and then we rearrange it to be lambda equals velocity over frequency. So now we have this equation, and now we can sub in the values. So lambda equals velocity over frequency. We can sub in the values to be lambda is equal to 3 times 10 to the power of 8, so velocity, divided by 200 times 10 to the power of 9 to be 1.5 times 10 to the power of negative 3 meters, which is also equal to 0.0015 meters. So now let's look at this, 0.0015 meters. Well, what is 15 centimeters? 15 centimeters is 0.15 meters, right? So is the wavelength below 15 centimeters? Well, yes, it is. It's a lot below 15 centimeters. So we have identified wavelength. For these types of questions, you need to have a sentence after you're working out. So what I would say is we've identified wavelength now. So now we need to actually answer the question whether the inspector should be worried. So we now say, we don't just say now the inspector should be worried. We say now we need to use the data that they've given as well. So we say as the wavelength is below 15 centimeters with a magnitude of 0.0015 meters. So this sentence over here, this first part of the sentence now uses the information that they've given us in the question. So I've used 200 gigahertz. I've used the velocity of a microwave, and now with this sentence I've used all of the data that they've given us in the question. So it really shows that I'm unpacking the question. So I say as the wavelength is below 15 centimeters with a magnitude of 0.0015 meters. So I refer again to the data that I have obtained from my calculations to once again solidify my sentence response. So I say as the wavelength is below 15 centimeters with a magnitude of 0.0015 meters, the inspector should be worried, basically because the wavelength is lower than the threshold of 15 centimeters. So that's kind of how you would answer this question. Yeah, so that was a couple of wave questions using the equations that we've learned, which is V equals F lambda. So that's just kind of the questions that you should be prepared to, or you should be, we're trying to expose you to, so you'd be more prepared for when these questions come up in school. So I hope that you guys, you are fine with those questions. And if you have any, questions so far with the questions, or you want a reclarified explanation, then, I'm in the text chat, the live chat, scouring through your questions right now. So be sure to post your questions on the chat, and yeah, I'll try and respond to all of them as soon as possible. So now that we've finished through that question set, we're going to be going through specific examples of wave behavior in terms of sound waves, and we're also going to be going through the Ray model of light. So these are the next parts of the module, but it all interrelates together. But yeah, let's go through the specific examples of wave behavior now. You might know some of these as well. So let's look at this. So we have reflection, diffraction, refraction, and superposition. So let's go through each of them now. What is reflection? Well, I'm pretty sure most of you guys would have heard about reflection, like, just the word itself. So reflection is when light, hits a surface and then reflects off. So it just bounces off that surface, right? And what's important with reflection is the angle made with the normal of the incoming wave is equal to the angle made with the normal of the reflected wave. Another way of saying this is the angle of incidence is equal to the angle of reflection, or the reflected angle, basically. So what is the normal? The normal is basically, think about it as an imaginary line that runs perpendicular to the direction of the plane that light is hitting. So if light is hitting a horizontal plane like this, then if it's hitting a horizontal plane like, I hope you guys can see this, if light like this is hitting a horizontal plane like this, then the normal will be perpendicular to this plane, so the normal will be vertical. Same way, if I now choose a vertical plane and light is hitting like this, then the normal will be perpendicular to the direction of this plane that light is hitting. So this normal will be now horizontal. So let's look at this example on the slides, right? So the plane is horizontal, so the normal is vertical. So light is incoming like this. So this is the incident light ray of light. What this law is saying is, or this dot point, what it's trying to say is, this initial angle, so the angle of incidence over here, is equal to the angle of reflection, or the reflected angle over here. So the angle made with the normal of the incoming wave, so the angle between the normal and the incoming wave, this angle over here, is equal to the angle between the reflected wave and the normal, so this angle over here. So that's what you need to take away, and I hope you guys understood what that means in terms of explaining reflection. So Now let's go through diffraction. So by definition, diffraction is the property, a wave property that describes the bending of waves around small obstacles or when a wave passes through a slit. And essentially when a wave passes, so over here now, remember when I was talking about wave fronts? So these horizontal lines show a wave front. And if I talked about it before, basically what I meant is, so you know how I mentioned that these are just, a line that you draw between troughs, sorry, not troughs, crests of multiple waves. So this is just a line that's drawn between the crests of many different waves. So, and I also talked about the direction of the wave is going to be perpendicular to the direction of the wavefront. So if we look over here now, the direction of the wavefront is this way, so it's vertical. So the direction of propagation, or the direction that the wave is traveling at, is going to be perpendicular to it. So the wave is going to be traveling this way. So that's where the arrow points. The arrow points to the right. So the waves are traveling to the right now, and it's hitting this barrier with two slits in it. So what happens now? Does the wave stop? Does the wave disappear? Well, no, it keeps going. So how does it keep going? Well, the points where the slits are, this wavefront now, it bends through these slits now. So the waves over here, it bends through these slits, and what it ends up creating is it creates point source waves. So this point over here where my cursor is, and this point over here where my cursor is, they end up creating point source waves. So if you see over here now, the wavefront is the wavefront is a straight line over here, and over here it's now circular, right? It's cyclical now. This wavefront, it's bent now, it's circular. So this shows us that point source waves are created. And if you look at the pattern of waves created, it's like a ripple in water, right? It's circular wavefronts. So that shows us that point source waves are created. And we also have something called wave interference, which is another property. And how can we tell that there's wave interference here? Well, the wavefronts of these 2 point sources interact. So this entire area where these 2 lines interact is where wave interference occurs. And we'll talk about wave interference later. You can see a little bit about it in the superposition tab, but we'll leave this now and we'll go to refraction. So what is refraction? Well, the refraction is, by definition, the bending of light as it passes from one medium into another. And the important thing is these 2 mediums need to have different refractive indexes, which is basically like, it just basically tells you how much light will refract within that medium. So the mediums have to be different densities, different materials, so that light will refract differently in both of them, and then we'll see refraction. Yeah, the bending of light as it passes from one medium to another, or alternatively, how hard it is for light to move through those mediums. So let's look at this, right? So let's look at this mathematically. So we have the angle of incidence, we have the angle of refraction over here. So this is the angle of incidence, this is the angle of refraction. This is, the normal again, because it runs perpendicular to the object, that it's the plane of the object. So the normal is the dotted line over here. And if you look over here, this angle and this angle should be mathematically same. It should be equivalent. So these angles of refraction should be equivalent. And we also have the emergent angle over here and the angle of incidence. So what this diagram is showing is the air surrounding this glass, or this block, basically the air surrounding this block should have a different refractive index to the material that this block is made out of, because you were observing refraction. So light isn't traveling straight through in a straight line, it is bending, and then as it leaves, it's traveling in that same direction, that same straight line, or that same straight line. So yeah, light bends within that box, and then it continues in that same straight line after it exits that box. That is an example of what refraction might look like. And in terms of where we see this, right, we see this is like, say you go to like a wishing well, basically, and you throw a coin in there, right? We see a coin like in front of us. Now, if we try and reach into it, we'll miss the coin. Why is that? Well, because we're seeing a refracted, light is getting refracted through the water. So what we're seeing is, we're seeing the coin to be either closer or further away from us. I'm not sure which one it is. I think the coin seems further away from us, I think. So in reality, I should appear closer to us, actually. So the coin appears closer to us than where it actually is, because it's being bent. So because it's being bent in the water, because water is a different medium to air, and water has a different refractive index to air. So the light that we see like coming out of reflecting from the coin that's exiting the water, it's actually being refracted, right? So that light that's coming from the coin is being refracted, and so when we reach to grab it, we'll actually miss the coin, because we're not aiming in the right position, because the light is refracted, it's being bent. So like, it's showing a position where it's not actually at. So the coin is going to be a little bit further away than where we reach to grab it. So yeah, that's kind of like a cool, like, real life application of refraction. But yeah, Now we can move on to the next dot point, which is superposition. So what is superposition? Well, it's a form of wave interference. It's where the peaks of the waves overlap. And what happens is, because the peaks of the waves are overlapping now, it forms a bigger wave. So it undergoes something that's called constructive interference. So when the peaks overlap, so if the peaks overlap, that means the crests overlap with the crest and the trough overlaps with the trough. So they're like, in line with one another, then they will add with one another to form a bigger wave. What happens is now when a crest of a wave meets a trough of a wave, so when the peak meets the dip of a wave, they will add again, but because when they're adding now, what happens is one wave will get subtracted from another one, so we'll end up getting a smaller wave. So we'll undergo destructive interference, and that kind of makes sense logically as well. If they're in phase now, they'll undergo constructive interference. If they're out of phase, so if the crest is now with the trough, it will undergo destructive interference because now they'll subtract from one another. So yeah, that's kind of what superposition is. So these are now 4 wave properties that you've learned. And again, if you're trying to memorize these, a good technique would probably to be after this lecture, after reading the slides over again, you might want to just, write down reflection, refraction, diffraction, superposition, and try and identify or like define it as much as you can. And try and see how close you guys got to defining these wave properties, and keep repeating this over, spaced intervals to try and recall the information and solidify this in your memory. So yeah, 4 wave properties right here. Now, let's look at some more stuff. So we have driving frequency and natural frequency. So driving frequency is the oscillations or the vibrations caused by an external energy source. So an external excitation. So if let's think about this. So if a opera singer starts singing, what's happening is that opera singer is supplying a driving frequency. It's providing an external source of excitation, so it's causing these particles to oscillate even more through an external form of oscillation, or its external form of excitation, basically. Same with natural frequency. Natural frequency as opposed to driving frequency is where the frequency of that object naturally. So the frequency as in the rate at which the oscillations of these particles normally. So every particle is vibrating, right? Even in solids, liquids, and gases, they're all vibrating, right? So these vibrations are what causes the frequency, the natural frequency of an object. And what happens is we supply a driving frequency that equals the natural frequency. Sometimes objects can explode, or sometimes objects can collapse or break, and this is what happens to stuff like buildings and bridges, right? If the transfer of energy within the system is at its most efficient point, where the driving frequency or the external excitation that's supplied equals the natural frequency, then that object can collapse, basically. So this is kind of what happens with opera singers. So if they sing at a high enough frequency, it'll equal the natural frequency of glass near them, and what will happen is they will end up shattering the glass, right? Because the driving frequency will equal the natural frequency, and will have the highest transfer, the most efficient transfers energy within the system, and it will cause the medium through which that energy is transferring to collapse. So yeah, that's kind of driving frequency and natural frequency. And the amplitude of motion now relates to the energy of the system. So that's another dot point that you should keep attention to. So yeah, those are some properties of driving frequency, natural frequency. Now let's look at progressive waves and standing waves. So what is the difference between the two? Well, thinking about the name, right? So standing wave, we're kind of stationary. So if we think of a standing wave, well, it's a wave that it appears stationary. So let's look at the definition now. A standing wave is a wave that travels forward and is reflected back, like when you generate a wave on a rope or a guitar string. So the wave it is stationary, so it's standing, and it appears to be vibrating up and down. So if I attach a rope to a wall and I try and move it now like this, what will happen is I'm generating a standing wave. So the wave travels forward and gets reflected back, and it just keeps being reflected back and traveling forward in that state. So what will happen is we'll get nodes and antinodes. So what are nodes? Well, let's look at this diagram, this GIF over here. So what are nodes? What are antinodes? Nodes are, so if we go over here now, if we go to, sorry, wrong slide. If you go over here now, if you look at this diagram, we have antinodes over here and nodes over here. Nodes are the positions where the wave is stationary. So the positions where the wave is stationary is called nodes. So we have these red dots over here, those are called nodes, and the points where the waves aren't stationary are called antinodes. So there's points where the wave is moving, these are called antinodes. So, and you can see this is happening because why are nodes and antinodes caused? Well, it's all to do with superposition, right? So let's look at this blue wave. The blue wave appears to be traveling forward, right? So let's say we're by spinning that rope now, we're inducing that blue wave. What will happen is that blue wave will will go forward and it will get reflected back, right? What is a reflected back wave? Well, it's the red wave. So we have the blue wave and we have the red wave. And these waves will interfere with one another. So take a look at this GIF. If you see now, when the crests align, so at this point, when the crests align, right, what will happen is it will undergo constructive interference. So you can see in this black wave, the black wave has the largest crest when these two crests align, when the blue and red when the blue and red wave align perfectly. So when their crests match each other and when their troughs match each other, what will happen is the waves will add to one another to perform to undergo constructive interference, and this wave the black wave will become maximized. The amplitude of the black wave will become maximized. Now what will happen if the crests now align with the troughs? So think about this point over here, right? What will happen is the highest point of the blue wave will align with the lowest point of the red wave. And since these two waves, the blue and red wave have equal amplitudes and equal wavelengths and everything, because they're just the same wave reflected in the opposite direction, what will happen is they will cancel each other out. So the crest will cancel out the trough and we'll get nothing. So that's where the nodes form. So it's basically, to our eyes, it's points of no movement. So that's kind of where this is all formed. And we can see over here, this point where it equals to 0, it equals to 0 where once again the crests align with the trough. So momentarily this black wave, it will become a straight line where the wave is completely out of phase with one another. So you can see it's moving right now, and at a singular frame, it will become a straight line and then continue to be a wave. That's where the waves are completely out of phase with one another. So those are nodes, antinodes, and how they are caused. Let's look at progressive waves now. So progressive waves are normal types of waves. So they travel forward in a medium and they transfer energy. Not too much to know about them. But yeah, now moving forward, let's look at different properties now. We have pitch and loudness, distance and sound, and we also have longitudinal mechanical waves. So pitch and loudness, so loudness of a sound wave basically is given by the amplitude of the wave. So the amplitude dictates loudness. Pitch, what dictates pitch? Well, what dictates pitch is frequency. The higher the frequency, the higher the note, the higher the pitch. So that's how that works in terms of pitch and loudness. All right, so let's go through distance and sound. So let's go distance and sound. So the volume or amplitude or the intensity of the wave, it decreases by the square of the distance the way you measure such here and next. So this is called the inverse square law. So if I'm standing 1 meter away from the source and I hear the sound with an intensity of I, or an intensity of 1, so if I'm 1 meter away from the speaker and I hear the sound with an intensity of 1, what will happen if I move 1 meter away, right? So if I move now to 2 meters away from the speaker, so I was initially at 1 meter away from the speaker, and now I move 2 meters away from the speaker, I'll hear the intensity not at half, I'll hear the intensity at a quarter now. So I initially heard it at an intensity of 1 when I was 1 meter away. So when R was 1, I heard it at an intensity of 1. So 1 over 1 squared is equal to 1. But now when I move an extra meter away, so now I'm 2 meters away, what I'll get is 1 over 4 squared is equal to 1 over 4, right? So intensity is proportional to 1 over R squared. So when I move 1 extra meter away from 1 meter to 2 meter, the intensity will become 1/4 of what it was initially. So this is the inverse square law, and you can kind of visualize this because the area that it covers increases, right? It's like a sphere basically. The area it covers constantly increases as the distance as our distance between that sound source also increases. The area that it covers also increases, so it expands basically. So that's how we would dictate distance and sound as well. So now moving forward, let's look at longitudinal mechanical waves. So longitudinal mechanical waves, they require a medium to travel through, so like a mechanical wave basically, and the peaks are given by compressions, so compressions over here, and the troughs are given by rarefactions. So the rarefactions are the areas of low pressure. So if we look at the slinky again, where the slinky coils were bundled up, those are compressions, and where they were less bundled up were the rarefactions. So those were the troughs, and the peaks are these points of high compression, or given by compressions basically, and the direction of travel is this way. So that's how we would unpack a longitudinal mechanical wave. All right, so now let's look at some more wave properties: diffraction, superposition, and reflection again. but this time of, well, mechanical waves this time. So diffraction and superposition. So it's essentially the same for mechanical waves. So yeah, it just the wavefront you can see entering this object with a slit inside of it, and the waves will basically, or the wavefront will basically bend through this small slit. And in terms of superposition now, we can see constructive and destructive interference, right? So superposition is once again a wave interaction basically, or wave interference. And we can see constructive and destructive interference here. So the points where there's, black shadows over here, that's where the waves cancel each other out. So if we're thinking about light now, which is, not a mechanical wave, but we're thinking about light now, the points of shadows over here are where there's no, or like close to zero intensity of light, right? And why is there close to zero intensity of light? Well, the two light waves probably canceled each other out, right? And that's due to, if you think about what we learned about in the past, will these shadows be caused by constructive or destructive interference? They'll be caused by destructive interference, because the crest will match with the troughs to, subtract each wave from one another. So they'll be out of phase. They'll subtract from one another. Destructive interference. We'll get shadows. Now, these white spots, are those caused by constructive or destructive interference? Well, it's the opposite now. It's caused by constructive interference, where the crests align with one another and the wave becomes, it becomes bigger now. So we extend the intensity of the wave, or the intensity of light produced by that wave, and so now we get bright spots. So this is constructive interference, the bright spots. So these bright spots are all constructive interference, and these dark shadowy spots are caused by destructive interference. So that is wave superposition. Now let's look at reflection, right? So reflections of sound waves now are what causes echoes, right? So, echolocation is basically, they send out a sound wave, it hits an object, gets reflected back, and animals basically process that reflected back sound wave, and by knowing the speed of sound, they can identify the distance between that object and itself, so it can map its surroundings using echolocation, basing reflected waves basically. And in terms of what it looks like, in terms of modeling what it looks like, the wave just hits the object and gets reflected backwards. So that's kind of what it looks like. So this is reflection, diffraction, and superposition in more detail. So now you guys should know how to answer basic wave questions. You guys should know, wave properties. What else you guys know? Well, the distance, or how the intensity of a wave fares as the distance between it and the sound, the distance between the observer and the sound source increases. So the inverse square law given by this formula over here. What these mean. So what is this dark area of, high compression? It's called compressions. What is this area of low compression? It's called rarefactions. This is also the high compression area. It's also called the peak. The low compression area is called the trough. What else? Progressive wave, standing waves. That's also something that you should know, where the nodes and antinodes are. And yeah, now we can move on to harmonic frequency and standing waves. So sound standing waves are created by bouncing waves back and forth in a closed pipe. So we have a sound wave, we bounce it back and forth in a closed pipe to create sound standing waves. To create harmonics, what we do is we have a standing wave with certain number of wavelengths. So we know the certain amount of wavelengths, and what happens is the first harmonic has half a wavelength of that standing wave. The second harmonic has so on and so forth. And so the open columns and guitar strings, closed columns are different to harmonics, right? But open columns and guitar strings are harmonics, and closed columns are slightly different to harmonics. But yeah, harmonics are like that kind of pattern that follows. So we have a standing wave with a known amount of wavelengths. So the first harmonic has half a wavelength, and so on and so forth. In terms of physical characteristics, story time now. A little bit like an experiment that I did in my school at NSB was one examination that they did it was quite a fun project actually. They got us to build our own instrument. So we were studying about waves and harmonics and stuff, and what they did was they got us to build our own experiment and do a depth study or like a prac report basically on how we built that and how we made the harmonics and stuff. So we got to talk about harmonics, how that worked, and we also did an experiment, or like we did a prac work on it. We built our own instrument. So let's look at the physical characteristics. That's kind of where it links into, right? So the physical characteristics, so the length of the pipe or the string, that determines how many antinodes appear, and the speed of the waves in the medium, the speed of the waves within is characterized by like the medium that is used. So a more dense medium, it will travel faster because it's sound compared to a less dense medium. So the next properties of waves that we're going to look at is beats and the Doppler effect. So what is beats, right? So after this, we should be going through some more questions as well. So to, apply the knowledge that we've learned so far. So we're also now entering some more equations. So equations means this can be tested in calculation questions. The rest of these, they could be tested in calculation questions using what we already know about wavelength and stuff. But mostly it will probably be conceptual and long response questions. So beats now. This is where the sound waves interfere and they create soft and loud alterations called beating. So basically when the waves are, they're not in phase, so you can see the red and green wave, they're slightly out of phase, and that'll end up creating beats. So if we look at the net wave that's created from these two waves being out of phase, we can see that beats are created. And the equation that we can use is we can model the beats by trying to find the frequency of these beats that we hear. The frequency of the beats that we hear is the absolute value of the wave 1 minus wave 2. Because the frequency is always positive, we take an absolute value, and we take an absolute value because it doesn't matter how we subtract the two, because the frequency of the beat always has to be positive. So we take an absolute value, and in that sense, we don't need to care about which one we subtract from one another. The bigger or the smaller, it doesn't matter because we take an absolute value of it to get a positive number for frequency. So yeah, that's the frequency for beats, and that is a formula that should be on your data sheet as well. Now the Doppler effect. So some of you guys might have heard this, but yeah, if you think about you standing stationary and you hear an ambulance coming towards you and leaving you, right? How does that ambulance sound in both cases? So think about when it's coming towards you and think about when it's going away from you. So when it's coming towards you, right, it would appear more high pitched, right? As a car or maybe an ambulance comes towards you, it appears higher pitched, right? Well, why is that? Well, the sound wave is moving towards us, right? But the source of the sound wave is also moving towards us. So what happens is, because the source of the sound wave and the sound wave itself is moving towards us, the wavelengths get squished. And as the wavelength gets squished, the frequency increases. And because frequency is related to the pitch increases as well. And so we hear a higher frequency or a higher pitched noise when the car or the ambulance is coming towards us. What happens when the car or the ambulance is going away from us? Well, the source of the sound is going away from us, but the sound wave itself is going towards us. So what happens is the wavelength now gets stretched, the frequency decreases, and as frequency is still related to pitch, we hear a lower pitch sound as it leaves away. So as it comes over here, it is higher pitch, so it sounds higher, and as the ambulance is leaving us now, we get a deeper sound in terms of the noise that we hear from the ambulance. So that practical application is derived by the Doppler effect. And what is the equation for the Doppler effect? Well, you see it over here. The observed F is equal to V plus V naught over V minus Vs times the frequency. So let's unpack this equation. So we have F dash, which is equal to the observed frequency. So the frequency that I will observe or hear as an observer is F dash. Of F, the frequency in purple, is the actual frequency of the sound wave emitted by the source. So the actual frequency of the sirens of the ambulance, that's F, the actual frequency. V is the velocity of the sound wave, so the 340 meters per second, so the velocity of sound waves in general. V naught, or the velocity of the sound wave in this case. V naught is the velocity of the observer, so if I'm stationary, V naught will be 0. If I'm moving, V naught will be moving as well. And Vs is the velocity of the source, so the source is the thing that's producing the sound wave. So in this case, in this example that I gave, the source will be the ambulance. So that is how we unpack the question, and that is Doppler's effect right here. So now let's go through a couple questions. So our first question: a drag racer speeds past a man standing at a crosswalk. The drag racer is traveling at 40 meters per second with its engine sounding at a frequency of 450 hertz. What frequency does the man hear as the drag racer approaches, and what frequency does he hear as it races away? Assume the speed of sound is 340 meters per second. So, like all our previous questions that we've done, let's unpack the question. So it's asking for two answers, right? First, when it approaches us, and first, when it leaves us. So let's answer the first part, as it approaches us. So as it comes towards us, right? What do we have? Well, the drag, so we are the observer, right? So the drag race is traveling at 40 meters per second with its engine starting at a frequency of 450 meters per second. So a drag racer speeds past a man standing at a crosswalk. So if I'm standing at a crosswalk, what is my velocity? My velocity as an observer, so I am the man in this case, right? So as an observer, my velocity is 0. So what is, if you go back now, what is V naught or V0? It's 0. So V naught is equal to 0. So we have that. So we have the blue one. We have a value for blue velocity. What else do we have? Well, we have the drag race is racing at 40 meters per second. So we have the velocity of the source. What is the velocity of the source? 40 meters per second. So we have green and we have blue. So these two are done. Now let's look for red. So let's look for red. So what is red? Red is velocity of sound waves. What is the velocity of sound waves? Well, it says assume the speed of sound is 340. So we have velocity of sound to be 340. So we have red, blue, and green. What else do we need now? We need to find purple, right? We need to find purple to find f dash. So what is purple? Well, the purple is 450 hertz, right? Because it says the engine sounds at a frequency of 450 hertz. So the actual frequency is 450 hertz. And we're trying to find F dash, which is what our observed frequency would be. So we have purple, red, blue, green. All we have to do is sub it in. So this is what it looks like now. So what we do is we first write our formula. So F dash is equal to F times velocity of the wave plus velocity of the observer divided by velocity of the wave minus velocity of the source. Now we just plug in the data values. Plug in the data values to equal 450 times 340 plus 0 over 340 minus 40, which is equal to 510. Okay, so now let me tell you why I plugged in the values the way I did it. So there are a couple of different ways to plug in the data sets, right? I could do 340 plus 40, or I could do 340 minus 40. They would yield different answers, right? Let's sanity check this now. So as he's moving towards us, will I hear a higher or lower frequency? Well, let's think about the Doppler effect in theory, right? As he's moving towards us, it's sending sound waves towards us, and it's also, the source is also moving towards us. What does that mean? Well, it means that the wavelengths are going to be compressed, and as the wavelengths are compressed, the frequency will increase, and so we should be hearing a higher pitched sound or a higher frequency sound. So as it's moving towards us, the frequency should be higher than the actual frequency. And does that answer correlate, or does that answer match our philosophical or understanding, our sanity check? Well, it does match the sanity check because our obtained frequency is 510 hertz, which is greater than the actual frequency of 450 hertz. So in an exam, you should be pretty confident in knowing that this is probably the answer, because it matches our understanding of what it should actually be in real life. It should be a higher frequency, and we got an answer of a higher frequency. So that's just a way to sanity check your questions. Now let's do the second question. Let's do a way. So again, we use the same equation. F dash is equal to F, which times velocity of the wave plus velocity of the observer divided by velocity of the wave minus the velocity of the source. And all we have to do is we have to plug in the values now. So we get 450 times 340 plus 0 over 340 minus, this time, negative 40. So you can see here how it differed from the way I subbed it in. This time, instead of subbing in 40, I subbed in negative 40. Well, why is that? Well, because I treated the source coming towards us as positive and going away from us as negative. So this time velocity becomes negative. And what does this actually look like? It makes our frequency smaller than the actual frequency. And is that correct? Well, let's sanity check this again, right? So as the drag race is moving away from us, the source of the sound is moving away from us, but the sound wave is still coming towards us because we have to hear it, right? So the wavelength then becomes stretched out. And as the wavelength becomes stretched out, the wavelength becomes larger, so frequency now becomes smaller, and so the frequency that we hear it at, the observed frequency, should be lower than the actual frequency. Does that match our answer? Well, it does, because we get an observed frequency of 400 hertz, which is lower than the actual frequency, so it does match our answer. Another important thing is you need to match this correct amount of significant figures, and I would also write a second sentence saying, therefore, as the drag racer approaches, the man will hear a frequency of 510 hertz, and as the drag racer leaves, the man will hear a frequency of 400 hertz. Just to answer this, these two questions, I would do my calculations and then write a sentence at the end that actually answers the question. So that's just how I would approach this specific question over here. Now let's go into the next question. So Adam and Arnold are playing the flute together. Arnold's flute is out of tune, so when he plays along with Adam's hits the A note at a frequency of 440 hertz, a beat frequency of 5 hertz is heard. If Arnold is playing slightly above Adam, what is the frequency of Arnold's A? Okay, so we know what the beat frequency is, and we know what F1 or F2 is. We know what one of the frequencies are, right? And we're trying to find the other frequency. So pretty simple. This is just how you do it. So we write down our equation. The beat frequency is equal to F2 minus F1, all in absolute value, just because, as I explained before, F beat has to always be positive, so we take an absolute value. And now it doesn't matter which one we sub it into. So we have one of the frequencies, we can sub it into either one of them. Doesn't really matter because, it could be, yeah, it could be any one of the two because we take an absolute value. And so now we have two possible answers. We have 435 hertz and 445 hertz. So which one do we pick? Well, the question tells us that Arnold is playing slightly above Adam. And if he's playing slightly above Adam, that means he's playing at a pitch slightly above Adam, and pitch correlates to frequency. So he's playing at a frequency slightly above Adam. So we need to pick the answer that gives us a frequency that's above Adam's. So we pick 445 hertz as the frequency that's above Adam, which should also give us a beat frequency of 5. So I'd do this and then I'd write an additional sentence saying, therefore, the frequency of Arnold's A is 445 hertz. Just to answer this final part of the question right here. So that's how I would approach this question. So let's talk about lenses, right? So we have concave versus convex lenses. So a concave lens looks like this, a convex lens looks like this. So a convex lens looks like this, a concave lens looks like this. A concave lens is like, caved in, so it looks like an hourglass. A convex lens is the opposite, it's like bulging outwards. So in terms of what will happen to light rays, they will enter the convex lens and then will be focused. So if you think about a magnifying glass, right? A magnifying glass has a convex lens. So you can also feel like the bulging in a magnetic glass, or a magnifying glass, sorry. And it's quite dangerous to focus the light on a magnifying glass because it can set something on fire, or it can burn you, right? The reason for that is it takes all these light rays and it focuses it on one point. So it focuses all the light on one point. And that's quite dangerous because, the intensity of the light or the energy carrying by the light is now all focused in one point. And that's why it's very easy to set a piece of paper on fire if you, directly shine sunlight through a magnifying glass onto a piece of paper, because it focuses all that light into one point. And that's also how magnification works. So because it focuses all of that light onto one point, it makes it makes us processing that data a lot easier, because now we can, essentially what it does is it magnifies the image. So reading glasses will also have convex lenses because it enlarges the image that we're basically reading, or we're trying to read. Now let's look at concave lenses. So what concave lenses does is, as the light ray approaches the concave lens, it will scatter the light rays, so it will make the light rays expand outwards, and that's kind of what concave lenses do. So now let's look at lenses. Now let's look at mirrors, right? So this is what a convex mirror looks like. This is what a concave mirror looks like. So a convex mirror will cause light to reflect off of it, and as it reflects off of it, because mirrors reflect, they don't refract through it. So this is called refraction, this is called reflection. This is refraction, this is reflection. So mirrors reflect the light back at us so we can see ourselves. So in a convex mirror, the light will be reflected outwards. So it's reflected outwards over here, whereas in a convex mirror, it's reflected outwards, whereas in a concave mirror, it's reflected inwards. So you can see over here that the arrows are going inwards. So that's what happens when a concave mirror is used. So that is, reflection, refraction within concave and convex mirrors at concave and convex lenses. So now we can go into some questions. So we have Snell's law and total internal reflection. So Snell's law is a law that allows us to look at the relationship between the angle of incidence and the angle of refraction based on the refractive index of an object, basically. So if you look at Snell's law, we have n1 sine theta 1 is equal to n2 sine theta 2. So n1 is like the first medium, so the medium that light is starting off in. So it starts off in this medium over here with an angle of theta 1. And as it leaves, it enters a second medium n2 with an angle of theta 2. So it's looking at the relationship between the angle of incidence and the angle of refraction. And another important thing is the angle of incidence, the refractive index for air is always 1. So that's another important thing to remember. All right, so now let's look at total internal reflection. So about refraction, right? So refraction is, when light bends. But light doesn't bend at every angle. At a certain angle, light will just refuse to refract through. Light will just refuse to bend, and it will bend. It will just reflect back into the object. So when n1, so when the starting medium is when the refractive index of the starting medium is greater than the refractive index of the reflecting medium, light will bend towards the normal. So it will bend towards the normal. And what happens is, as we increase this angle, as we increase the initial angle, so as we increase theta 1, what will happen is it will hit a point where it will just refuse to bend anymore, and it will just go through total internal reflection. So that is called the critical angle, this angle where it just it bends towards the normal basically. So what will happen is, sorry, it won't bend towards the normal, sorry, it'll bend along the boundary. So we will keep increasing the angle, the initial angle, so theta 1, we'll keep increasing that initial angle until it reaches the critical angle, which we can denote through this formula over here. And when we reach that critical angle, what will happen is the light won't bend anymore. It will travel along the boundary. So it will travel along the boundary of the mediums. And as we increase the angle beyond the critical angle, it won't undergo any reflection anymore. What will happen is it won't undergo any refraction anymore. It'll undergo total internal reflection. So if you see here now, this is how light would occur between medium 1 and medium 2. So when the angle is less than the critical angle, it'll get refracted through. Some of it will obviously still reflect through. It will undergo some of it will undergo internal reflection, but most of it will undergo refraction. Most of it will bend, right, when the angle is less than the critical angle. As we keep increasing the angle now until the angle equals the critical angle, what will happen is it will travel along the medium now. It will travel along the boundary now, along medium 1 and medium 2, along the separating line. It will travel along that boundary. And as we increase it even more, what will happen is it will undergo total internal reflection. So all the light will be internally reflected. So this is like the content that you need to cover. So Snell's law and total internal reflection. And in terms of total internal reflection, always remember the critical angle. And always remember that if it's greater than the critical angle, that's when total internal reflection occurs. So now let's look at dispersion. So another bits of light phenomena or light wave phenomena. So dispersion is what happens when light can undergo dispersion. So it'll enter this prism over here. So you might do this in class as well. And what will happen is the longer wavelengths of light have a lower refractive index. So they bend, the lower wavelengths of light, which is red, the lower wavelengths of light. What will happen? So the lower wavelengths of light will bend less, and so they will, whereas the higher wavelengths of light should bend more. I'm pretty sure that's how it works. Yeah, so the higher wavelengths of light should bend more, where the lower wavelengths of light should bend less. And what will happen is, because of that, and because white light is made up of, tons of different wavelengths of light, they're made up of all different colors of light, right? And each color has its own different wavelengths. So these wavelengths bend to different extents. And because of that, as it enters this prism over here, it spreads out, right? So you can see that light is a single line. And as it enters the prism, because they all refract to different extents, it starts to spread out, and as it leaves this prism now, we can see it in different colors. So it spreads out, and because of that, it produces a rainbow pattern, because now we've extracted the colors out of that white light basically, and so we get to see different colors. So that is dispersion over there. And also the inverse square law, which we were talking about earlier with regards to the intensity. So the area of the light increases by square of the distance, and energy transfer is constant, however, but we can compare intensity at 2 points by I1R1 squared is equal to I2R2 squared. So if we're looking at this analogy over here, so this is what it looks like. So let's say at 1 meter away from a light source, I have an intensity of 1. If I'm now 2 meters away, I have an intensity of 1/4. So that's kind of how this inverse square law works, and that's kind of the example that I was referring to previously. So yeah, that is light phenomena now. I think we go through a final set of questions now. So let's go through this question now. And then we'll go through thermodynamics. But before that, we'll go through this final bit of module 3. So a specially refined block of perspex is tested for its refractive index. The speed of an X-ray traveling through it is measured at 230 million meters per second. What is the refractive index of this special form of perspex? Okay, let's go through this now. So we have velocity of X-rays in the air. That is equal to 3 times 10 to the power, or in vacuum basically, is equal to 3 times 10 to the power of 8 meters per second. So that's the normal velocity of an X-ray. That's C, basically the constant C. Now we have velocity of X-ray in perspex as 2.3 times 10 to the power of 8 meters per second, right? So there's obviously a difference in velocity. It slows down because perspex is probably denser than air. So now we know that the refractive index is greater than 1 as it slows down. So as light slows down, that means it's entered a more dense medium. So sanity checking now, we should know that the answer that we get should be greater than 1. So now let's calculate it. So refractive index is basically the ratio between these two. So if we're trying to find the ratio between those two, we just do 3 times 10 to the power of 8 meters per second divided by 2.3 times 10 to the power of 8 to get 1.3043. And now let's sanity check, right? Is this greater than 1? Well, it is. So it is greater than 1. So it shows that the refractive index is greater. So it should, it should be more dense. Basically, it should bend more, essentially, or it should slow down more. So that kind of tells us that it's kind of aligning with our sanity check. So it tells us that our answer is probably right. And now to even more sanity check, I searched up the value for the actual value for the refractive index of perspex to have an average refractive index of 1.491. So it has an average refractive index of 1.491. And we got an answer of 1.3043, which is, pretty accurate given the data that we got. So we got simplified data and we got a value that's pretty accurate to the actual average refractive index of perspex. So that tells us that our answer is probably correct. So that is this question done. Now we can go into thermodynamics. So let's go through thermodynamics now. We have 3 different things: conduction, convection, and radiation. So conduction is, heat transfer that it occurs through contact between solids. So what happens is particles will bump into each other and transfer kinetic energy from one thing to another. So let's think about this. So if I now, I have innate body heat of like around 30 degrees Celsius, right? And if I touch my laptop over here, I'm going to see it's cool to the touch. So I touch the metal on my laptop and it's cool to the touch. Why is that? Well, first of all, I don't want you to guys have the concept of cold inside of you. Cold, it doesn't really exist. Something that's hot will have, does exist, but cold doesn't really exist because cold is essentially an object that is less hot than another thing. So what will happen is, if I'm explaining in this sense, hot, like how hot something is denoted by how much kinetic energy that the particles within that object has. So my 30 degrees, I will have a certain amount of kinetic energy in my finger. And because I feel this laptop, the metal in this laptop, to be less hot, what that will tell me is the kinetic energy in the particles in the metal within this laptop is less. So I have more kinetic energy in the particles that make up my hand compared to the particles that make up my laptop. So as I touch my laptop now, what will happen is the particles in my hand will bump into the particles in the laptop, and it will transfer that kinetic energy from my hand into the laptop. So now my hand will start to lose heat as I'm transferring the kinetic energy into my laptop, and my laptop will now begin to heat up as it's increasing in kinetic energy at the points where I'm touching it, because my particles are bumping into the laptop particles and sharing its kinetic energy with it. So that's kind of how conduction works. And that's how, so that's how, a pot begins to, we'll heat the pot at the bottom over here where my cursor is, and then we'll also start to feel it at the handle soon, because, that kinetic energy is traveling through the entire pot, so the entire thing is beginning to heat up. Now let's look at convection. So convection is a heating method that occurs through liquids and gases, and if you think back to convection currents, that's kind of also, linked to convection. So we have convection as the physical movement of particles from one place to another, buoyancy forces. So convection currents now. So this over here which my cursor is circling, is a convection current. So if I'm looking at this now, I have cold particles which are less dense. Cold particles which are more dense, right? So initially all the gas particles within that pot are, let's say they're cold, right? So they're cold. All the gas particles in this pot are cold. As I begin to heat it now, what will happen is the air at the bottom will begin to get heated up, right? The air at the bottom will begin to get heated up. And so it will start to become more excited. The particles will start moving more, and so it'll become hot. So what happens is hot air is less dense than cold air, because the air will probably be moving around more, so there'll be more space between the gas particles, and so it'll be less dense. And so hot air is less dense. Hot air rises because less dense air will go to the top, and more dense cold air will sink to the bottom. So the more dense colder air will now sink to the bottom. And what will happen is, as the more dense cold air sinks to the bottom and that hot air rises to the top, that hot air now will begin to cool down and become cold, because it's no longer close to the heat source. Whereas the cold air now, which is closer to the heat source, begins to heat up and become hot air. And so now the cold air that's now at the bottom will become heated up and become less dense than the hot air, which is now cooled down and become cold. So now there's cold air and hot air at the bottom again, and so it will continue, and so now it'll shift again. So now the cold air, which was hot before, will sink to the bottom again, and the hot air, which was cold before, will rise to the top. And this cycle will keep on happening to form what we know as a convection current. And then we also have radiation. So the thermal vibration of an object causes EM radiation to be emitted, and this is like, kind of relevant to, if you think back to the flame test that you did in module 1. So thermal vibration is also a form of an energy transfer. So it's a form of excitation as well. So we can excite something, it releases an electromagnetic wave in the form of light, which is also a form of radiation basically. So electromagnetic radiation is light. Visible light is a form of EM radiation. So it will release light, and that's also a form of thermodynamics as well. So hotter objects emit higher frequency electromagnetic waves. So if you think about, if you think back to like, I don't know, 2016, I don't know, like the 1,000-degree knife challenge, right? In YouTube, if you think back to those videos, right, you always have that image of a photoshopped glowing knife. Well, that knife is glowing at 1,000 degrees Celsius because it's so excited that it's releasing visible light at a wavelength that we see or we interpret as orange and reddish. So that's the wavelength that it's emitting light at because it's excited. So it's releasing EM radiation at a wavelength that we see and interpret as orange visible light. So that just shows that hotter objects emit higher energy, or hotter objects emit electromagnetic radiation as a form of, like it's just a form of radiation that's emitted when something gets heated. The other thing is, some objects, they don't glow. So even though objects have heat, they don't glow because the radiation that they'll emit is going to be too low, or it's going to have such low energy that it's not going to be in the visible light spectrum. So everything does emit electromagnetic radiation to different intensities, but sometimes they carry such less energy that we don't see them in the visible light spectrum. That's only why when you heat up a metal, it'll begin to glow, and that'll show us that it's emitting now orange light. So that's just kind of how that works. Now let's go through some more questions. So some more equations, which means we're going to be doing some questions now. So latent heat and thermal conductivity. So solid to liquid is called fusion. Liquid to gas is called vaporization. And latent heat is called energy involved in the changing state. So latent heat is the energy that's required, or energy involved in something changing state. And what happens is, so the temperature stops changing, but the energy just increases. That's also just a property that you should know when it's changing state as well. So now let's go through thermal conductivity, which is the most important part on this slide. So thermal conductivity K is the ease at which a material conducts heat. So it is a constant K. And we have Q over T is equal to Ka delta T over D. Q over T is the rate of heat transfer. So Q is given in joules, T is given in seconds. So joules per second is the rate of heat transfer. We also have area, which is the surface area of this object that heat flows through. We also have change in temperature, which is the temperature difference. And we also have D, which is the thickness of the material. So those are just like the equation, or like the breakdown of the actual equation. With that, now we can go into the actual questions. So how much heat energy is needed to increase the temperature of 300 grams of water from 1 degree to 100 degrees Celsius? Give C of water equals 4.81. Given C of water equals 4.81. So this doesn't actually use our thermal conductivity equation. What it uses is a second equation called given by Q equals mc delta T. So the energy joules required to heat up something is given by Q is equal to mc delta T. So let's break down this equation. Q is given in joules, energy. M is the mass of the object that we're heating up. C is it's like a constant, the energy heat constant, something like that. That basically tells us, how likely it is to get heated up, or how willingly it is to get heated up. So this, the constant for water is 4.81, but everything, other objects will have different constants. And delta T is given by change in temperature. So the energy required to increase the temperature of something, or change the temperature of something, with a given mass. That's kind of what this equation is showing. So we have Q equals mc delta T. We can slot everything into that equation, right? So we're trying to find Q. We have M, 300 grams. We have C, 4.81. And we have change in temperature, which is 100 minus 199. So we have our data, 300, 4.81, 99. All we have to do is we have to sub it in. So Q is equal to 300 times 4.81 times 99, which you should get a value of 1.42857 ... times 10 to the power of 5 joules. So yes, a lot of joules to heat something to boiling, basically, to heat water to boiling from 1 degrees. And now we should simplify this to the lowest amount of significant figures. So what is the lowest amount of significant figures? Well, we have 1, 3, 3, 3. So obviously subjective here because we have 1 and 3. So which one is the lowest amount of significant figures? Well, I'm still going to pick 3 in this case. So I'll pick 3, but some schools, they might want you to pick 1. But yeah, I pick 3 and I get 1.43 times 10 to the power of 5 joules to 3 significant figures. So that is my answer over here. And obviously, I'll write a second sentence saying, therefore, the amount, so we need 1.43 times 10 to the power of 5 joules of heat energy to increase the temperature of 300 grams of water from 1 degree to 100 degrees Celsius. So I'll write that one sentence afterwards to directly answer the question. So that's how I would approach this question and get my answer to that one as well. So let's go to the next question, which will require this thermal conductivity equation. So let's go through this now. A supercomputer needs to cool down through a heatsink, which has an area of 0.01 meters. So obviously it has area now. So I'm thinking, okay, what equation do we have that has area? The thermal conductivity equation. So I'm automatically thinking of that equation. And it has a thickness of 1.5 centimeters. It must allow 150 watts of heat flow through a component of temperature 75 degrees Celsius to a surrounding air temp of 21 degrees Celsius. What does the thermal conductivity of the heatsink need to be? Well, we have one unknown variable in this question, right? We have 150 watts of heat flow. That is an unknown variable. What does this, use of watts show? Well, this 150 watts is our Q over T. It's our joules per second. That's what watts is, and so that's what this 150 watts is telling us, that joules per second of heat flow, basically. So we have all the data that we need. So we have our equation, Q over T is equal to Ka delta T over D. We have A is equal to 0.01 meters, thickness D equals 0.015 meters, which is 1.5 centimeters. We have the change in temperature to be 75 minus 21, so 75 surrounding air temp and 75 temperature of the component to 21 degrees of surrounding air temperature. So our delta T, change in temperature, is 54. And our Q over T, which is the joules over time, or change in energy, is equal to 150 watts. So we have all our data. What do we need? We're looking for the thermal conductivity constant of the heatsink, which is K. So now we can rearrange the equation to make K our subject. So let's do that now. So let's rearrange this equation. So K is equal to, so what I did here was I divided both sides by A delta T, and then I multiplied both sides by D to get rid of this component over here to isolate K on one side. So K is equal to Q over T times D over A delta T. So now I've isolated K as like the subject of the, or like as like what we're trying to find. So we're subjecting K to the equation. So I've isolated K now. So all I have to do now is sub in these values to get a value for K. So I sub in these values now to equal 150, which is Q over T, times 0.015, which is D, divided by 0.01, which is A, times 54, which is the change in temperature. So 150 times 0.015 divided by 0.1 times 54, which is equal to 4.16666 ... And then we have our units over here, which is, watts divided by meters divided by Kelvin. So watts per meter per Kelvin. So that is our units over here. So I have my value for K in units as well. And I get 4.2 watts per meters per Kelvin to 2 significant figures. All right. Now we have, also one more thing, 2 significant figures, because the lowest amount of significant figures here is 0.01 and 1.5, which is, 2 significant figures. So I write 2 significant figures at the end, and I would say, therefore, the thermal conductivity of the heatsink needs to be 4.2 ... to 2 significant figures. So that's what my final sentence would say to directly answer the question. Okay, now